So for the previous lectures, we were focused somewhat on looking at linear circuits. So we were looking at RL fault transits, we were looking at capacitor switching, transit recovery voltage, and current chopping. In all those cases, we're making the assumption that we could take like the model for the line or the model for the capacitor or the model for the load that we're going to have load chop, current chop for, and model everything in terms of linear circuit elements. Now what we're going to do is we're going to take a look at transformer modeling. In particular, we're going to look at two nonlinear phenomena. One is transformer inrush and the other one is ferroresonance. And so what we're going to see here, this is going to take a little bit more work in order to try to figure out the appropriate model. And we're kind of getting to the point where we can't really simulate this by hand anymore. We generally have to use some sort of computer solutions in order to model these nonlinear types of effects. And so before I get into the material, I want to kind of talk about a use case where you would run into this. And one would be for looking at transformer inrush associated with photovoltaic systems, especially large ones. And the case I have right here is a situation where we have a large photovoltaic system that's at the distribution level. In this case, it's 20 megawatts, so it's a pretty large PV facility. And so what we have is we have a substation, and basically this is going to have multiple feeders connected to up on the low side. And so anyway, for this particular scenario, we got the substation, and the monitoring that we have in place is on the low side of this transformer. So we have two feeders. We have one feeder, this is feeder number 2, that has a photovoltaic plant, and then we have another feeder that has an industrial plant. And this particular industrial plant, the case we're concerned about, had a lot of process type load. And so what we would be worried about is if I had that photovoltaic system, what type of adverse power quality impact might it have on this industrial plant. And so one thing that's going to happen is when you have, say, like a fault somewhere on the circuit, let's suppose you had a fault out here somewhere, what would happen is we would have to disconnect this photovoltaic system from the grid. And so this would be done perhaps by operating this PV upstream breaker. When the fault's cleared, what we're going to do is we're going to re-energize that PV system. And if you have 20 megawatt PV plant, you're going to have at least 20 MVA worth of transformers there, right? And so what's happening in this case is all 20 MVA of that transformer capacity gets connected up in parallel. So this actually consists of smaller transformers. In this case, you would have had, say, like 10 2 MVA transformers being energized at the same time. But it's like having, the equivalent of 20 MVA being energized. And so what's going to happen in this case is we're going to get this huge amount of current that's going to be drawn to energize the PV system transformers. The thing you run into on this, though, is when we talk about transformer energization, that's going to be the subject of this lecture. What you're going to get is not just simply a steady state current. What's going to happen is we're going to get a large amount of current rushing into that transformer in order to magnetize that core. And because that core has nonlinear characteristics, what happens is, depending on the phase and the point on wave at which the energization happens, we're going to get these large current spikes. There's going to be non-60 hertz. It has a very rich harmonic content. And you can see that this lasts for kind of a long period of time here. So it takes a while for this to decay out due to the damping that we have in the circuit. And so these are actually field recordings that were taken at the substation. Now what happens is, if you have a large amount of current that's flowing into these transformers at the photovoltaic plant, well, the load on the adjacent feeders is going to see that impact because the substation has impedance associated with that. If you have a large amount of current going to that photovoltaic plant, it's going to cause a large voltage drop across that substation transformer, which is going to cause a voltage dip at the industrial plant. And so if you look at the recordings, not only do you see the current inrush, the fact that current spikes, but because it's interacting with the substation impedance, we see a voltage drop. And not only does a voltage drop, but that voltage drop has a large harmonic content associated with it. And so in this particular case, what happened because of this, since that customer saw this voltage drop with the large harmonic content associated with it, the motor drives, which were power electronic based, a few of those motor drives actually tripped out. And so obviously this would cause some power quality problems if these motor drives were powering some type of a process that was dependent on these motors turning at a constant speed. So anyway, because of this, what a lot of utilities are actually starting to do now when they do these large PV system interconnection studies is they're running this additional screening. They're actually testing to make sure whether this transformer inrush is going to cause a problem or not. So anyway, we can model this in PSCAD. We can actually simulate this in EMTP style programs. And what we actually see in this case is when we have this inrush, we see that one of the phases would tend to have a large inrush characteristic depending on the point of wave. And then you would see this in the other phases as well, not as bad, but you would nonetheless see this effect. And what this is going to do is this is going to cause deviations in the voltage. We actually get a little bit of a voltage dip associated with this. And this is going to be very rich in even harmonics. And so like second harmonics, fourth harmonics, because it's asymmetrical around the axis. And so when you have asymmetrical quantities like current, then this is going to be associated with even harmonics. So anyway, what we want to do is we want to take a look at two nonlinear phenomena. We'll start off with the transformer inrush, and we'll look at something called transformer ferroresonance. Then I'm going to say a few things about transformer modeling. This is a pretty big category in itself, so we're not going to get into a lot of detail. You can always look at the PSCAD reference manual for this. And then associated with the transformer inrush, I'll have a worked example, which will be in a second video. And then I'll take a look at how we model this in PSCAD and Simulink, and we'll have some examples in simulation for the inrush phenomenon as well as the ferroresonance phenomenon, and show you how you can model this using computer programs. So just as a review of the transformer model, we base this transformer model on having an ideal relationship where the ideal transformer, we have a turns ratio of NP on the primary side and NS on the secondary side. What you'll get is you'll get a transformation of voltage and you'll get a transformation of current. And when we model the windings in more detail, for the primary winding, we're going to have resistance, we're going to have some leakage where the flux leaks to the outside air. So that's represented by RP and LP. We're going to have series resistance and air leakage on the secondary side, represented by RS and LS. And then what's going to be nonlinear in this case is going to be the core model. And so we're going to be kind of focusing initially on this saturable reactor, or what we sometimes refer to as the magnetizing inductance. And this is going to be in parallel with an impact of core hysteresis, which is also nonlinear. But in this case, we're not going to be as focused on this, so we're just going to say this could be represented by a constant hysteresis and core loss equivalent resistance. All right. And so anyway, this is the base model, which you've probably seen before. And what we're really going to be kind of focusing on here is what is really the impact of having that nonlinear magnetizing reactance. Another thing you get into when you're doing this more advanced modeling is what's the core construction of the transformer. And this is actually going to make a difference when you do these more advanced sort of calculations. And so there's two types of construction, what we refer to as the core form and the shell form. A lot of times when we're doing our analysis, we kind of assume a core form. And so core form, if I had an iron core that's square, and, and if I'm going to have like a set of windings around the core itself, as shown here, then this is basically what we call the core construction. And your less expensive transformers typically would have this sort of construction. When we talk about a shell type of a form, what we're talking about is we're talking about a more elaborate design where what we're going to do is we're going to have the windings wrapped around this middle magnetic leg. It's a more expensive type of design, but that's actually what we would prefer to for our higher MVA transformers, because we'll get better performance characteristics out of that, even though it actually costs more. Okay, so a lot of times if we were going to talk about like MVA class transformers for say like PV plants, they would typically be more like the core form, but if you're going to see something in a substation, that might be more of a shell form. And so anyway, this kind of shows what this looks like in a little bit more detail. When we talk about three-phase transformers, you have what we refer to as three-legged, four-legged, and five-leg designs. And so for a three-leg stack core, what we would be doing is we would have three different legs where we would be wrapping the A, the B, and the C phase windings together to get coupling between the primary and the secondary side. All right. So like the primary and secondary for phase A would be on this one leg. There's other designs, four-legged and five-legged, where we have a fourth leg where we have an extra limb as shown here on the left, or we have an extra limb as shown here on the left and right. And the difference in these models has to do with the flow of flux. And so basically you're going to have for winding A, you're going to have a flux associated with phase A. For winding B, you're going to have a flux associated with phase B. And what differs in these cases is basically how the flux is going to circulate in these different types of three-phase designs. And where that makes a difference is if you have unbalanced sort of conditions, like say for faults. And so the fault model, the zero sequence model that you would have for a three-leg core would be different than what you would have for a four-leg core or a five-leg core. That's getting a little bit more than what we want to get into in this particular sort of course. But if you guys were doing more elaborate modeling, say if you're looking at microgrids and you're worrying about the impact of faults, this core model could actually make a difference. And so you would want to get into this in more detail as well. So anyway, what we're mostly seeing in a lot of these applications for like industrial and lower power utility applications are these three-leg stacked cores, and this gives you kind of an example right here. It's stacked in the sense that you basically have a number of plates, thin plates, and you're putting these plates together in order to make a core, and then you're going to have like your A phase, your B phase, and your C phase windings set up as shown here. So for the transformer magnetizing inrush phenomena, typically what we're looking at is we're looking at having a source that we switch on to the primary side, which I'm going to assume in this case is going to be side number one. A lot of times we assume that we're under a no load condition, so I2 is equal to 0. It doesn't have to be that way. I mean, we could actually have a load on the secondary side, but as far as looking at the transformer inrush, it's not really going to depend too much on what that I2 is, because that current's typically going to be have a pretty small effect as far as looking at this inrush. And so anyway, because this core has nonlinear characteristics, that's what's going to give us this large amount of inrush current that's going to happen when the switch closes in. And we have to be cognizant of the fact that it can close in on voltage magnitude or on a zero crossing or a voltage minimum, whatever. And we're going to get different results depending on that point of wave. All right, so what's going to kind of play into this analysis is going to be the number of turns we have. Something that's also going to play into this is what's going to be the cross-sectional area of the core, what's going to be kind of like the equivalent length of this particular core. That's all going to be kind of part of this problem formulation when we look at this. So again, what's going to be the basic set of relationships? Well, first of all, what we've got is we've got these magnetic circuit relationships for current and for voltage, and how they relate to the magnetic circuit themselves, which we talk about in terms of magnetic field intensity and flux density. And so one basic relationship that we have is to have, and this is for the direction of the currents I have shown right here, that N1, the number of terms times I1 minus N2 times I2 is equal to H times L for a non-ideal transformer. This term H is what we refer to as the magnetic field intensity. And if I had an ideal transformer, if this transformer were ideal, in an ideal transformer, this N1 times I1 minus N2 times I2 would be equal to 0, right? And so what this non-ideal relationship represents is the fact I've got to have some current flowing in order to magnetize this core, all right? And so let's make the assumption, when we're working this, that this magnetic field intensity is going to be uniformly distributed. Then we're going to have a relationship between these two currents where this is going to be equal to H times L, or as I mentioned before, L is going to be kind of like the length of this core. Now, this magnetic field intensity H, it's going to be related to the core magnetic flux density B by what we call core permeability, which is given by mu. And a lot of times, if we're talking about a linear circuit, this relationship between B and H, the magnetic flux density and the magnetic field intensity, is going to be given such that B is equal to mu times H. If we had a linear material, this mu term is going to be constant. However, in actual cores, when you start modeling the non-linearity, we've actually got a relationship that looks like this. And in this case, I'm not modeling hysteresis. But what we're going to have is we're going to have a relationship between B and H that looks something like this, where you note that it's going to be somewhat linear going up to 0.8 Webers per meter squared, or Teslas, that's another term for B. And then once we get above 1, then you can see this starts to saturate. And so a lot of these transformers in steady state are going to be operating such that the B internally is going to be about 1 Tesla. But once we get above a certain level, once we start cranking up H, which is going to be equivalent to the current, and B is going to be kind of equivalent or related to voltage. Once we start raising that voltage up, what we're going to see is we're going to need a lot more current for a given increase in B for the circuit right here. So this is a highly nonlinear sort of a characteristic, where if we stay in the low range, it's going to be fairly linear, but once we start getting up to higher and higher values of voltage in B, then we're going to see this saturation effect. Okay, so let's kind of try to piece something together here where we can kind of quantify this, because basically in the end what I want to do is I want to kind of figure out, if I energize this circuit, what can I expect for this current? How can I predict this current? So we want to have some quantitative relationships, and the way we start this off is we basically assume that this magnetic flux density B is going to be uniformly distributed across the cross-sectional area of this core. So if I take a cross-sectional of the core, B is going to be the same everywhere within the core. And what this means is I can model the flux. I can model the flux that's flowing by B times A. If I take the flux density and multiply it by the cross-sectional area, that gives me magnetic flux. All right. Now, Faraday's law says that if you want to calculate the voltage, the induced voltage, that this is going to be the number of turns times the change in this flux with respect to time, right? And so we're going to make use of that. We're going to make use of that later on. The voltage source that we're going to have that's going to be energizing the circuit right here, let's suppose this has a form of square root of 2 times Vm times sine omega t plus theta, where theta represents the point in wave. And so basically, if the switching occurs at time equals 0, then I can work with different initial values of voltage by changing this point on wave relationship, by changing that angle. All right. So what we can do then is we can start to, by Faraday's law, basically relate this voltage to this internal flux flow. And so what I'm going to do in this case is I'm going to start with this relationship, this Faraday's law, but now I'm going to solve for the magnetic flux. And so the magnetic flux that's going to be flowing in this core can be written as 1 over N1 times this integral, the voltage term. And what I have to add to this is I have to add a residual flux. This is basically a kind of like a residual flux that's due to the past operations of the device. And so if I had a core material, and if I wrap a winding around it, if I run a current through here, basically what I'm doing is I have an electromagnet, but what I'm doing is I'm orienting the magnetic dipoles in this circuit where the current's positive, then I'm going to have a north-south orientation. In other words, this magnetic core has memory associated with it. And so depending on how I de-energize a circuit, I'm going to have some residual flux that's going to be existing, which I have to kind of add into to get the total flux. All right. If I perform this integral, then I'm going to see that this magnetic flux with respect to time is going to be square root of 2 times Vm divided by omega times N1 times a quantity of minus cosine omega t plus theta plus cosine theta plus this residual term. So in other words, what's going to happen, depending on this value for theta, I'm going to get a time varying magnetic flux. And we'll just assume for now that we don't have to worry about the damping effect. So there's no damping in here just yet. And what we are also going to make use of is we're going to make use of the fact that in steady state, once this damping occurs, then the steady state flux is going to be such that this DC term is going to be disappearing. And so what we're going to have in steady state is a steady state flux of minus the square root of 2 times Vm over omega times N1 times cosine omega t plus theta. And so once we're in steady state, then we're going to have this relationship between voltage and the flux, where we don't have those DC terms anymore. It's just kind of like when you have in an RL circuit, the current DC offset disappears. The same thing is going to happen with the flux in the circuit due to hysteresis and eddy current losses. And basically, we're going to have a steady state flux that's going to have a magnitude that's given by square root of 2 times Vm over omega times N1. So now what I can do, if I want to figure out, say, like what's going to be the peak value I can have, what I could do is I could make use of this relationship for this maximum flux. I can substitute that into the equation on the previous slide. And for the case where theta is equal to 0, when I go through 1/2 cycle, in other words, when omega t is equal to pi, then what I can see is I can see that this peak flux is going to be square root of 2 times Vm over omega n1 times 2 plus theta r, where this particular quantity corresponds to the magnitude of the steady state flux. So what I'm going to have for a peak is actually twice of what I would have in steady state, plus whatever residual flux that I would have in the core. And the problem is that this peak value, this high peak value of flux, is going to correspond to a large magnetic flux density, which is going to correspond to a high value of current. So anyway, what I can do then is I can actually quantify this particular relationship right here. Since I know that this particular term here is going to correspond to the magnitude of the flux, what I can do is I can then have a time varying form here for this magnetic flux, and I can relate this to the BH curve and get the time varying current. So then what I would need to do is I need to go back to this BH curve. Okay, this is the curve that relates B to H. And in this particular case, if I assume that I2 is equal to 0, I know that I1 is going to be H times L over N1. And what I can do now is, if I have this value for flux, I can relate this to B. Once I have the value for B, then I can go to a point on the curve. I can pick off H. And then once I have H, I can relate this to I1. All right. So if I have this BH curve, there's actually a way I can actually map this to current now, and I'll show you in more detail how to do that in a worked example, which I'll be doing in the second video. But the issue here is that if I've got this transformer, and if all of a sudden I've got this large amount of current, there's a lot of bad things that are going to happen associated with this. One would be all these transformers have some type of protection on them. And so this could actually cause a relay to operate. So as it sees a large current, it might think it's a fault. It might cause a fuse to blow if the fuse isn't sized properly. As I mentioned before, if we have some impedance, and we're going to get a voltage drop across there, which is going to give us some distortion. Eventually this damps out, but what we're kind of looking at is what's going to happen during the first couple cycles of this, and whether this is going to cause any issues or not. So anyway, for this worked example, I kind of showing you a result of what this is going to look like. If I have a sinusoidal source, and let's suppose the switching occurs, the energization occurs at time equals 0. This is done for the case where theta is equal to 0. Basically, this is going to be the form of the applied voltage to that transformer. It's going to be kind of sinusoidal in nature. What's going to happen is the current's going to start changing, and then as I get into the nonlinear region of that curve, it really starts to rapidly increase. And then as the flux drops off, it drops back down again. But what we're going to see is we're basically going to see this cycling of current that basically has a DC offset, and then it's just simply going to be kind of changing every cycle as shown here. And then eventually what happens in a real circuit is these peaks start to die down and eventually go to 0. But the damping isn't such that we don't have to worry about what these peaks are. All right. And when I talk about relays and talk about how we're going to deal with something like this, the typical way you deal with this in a relay is you make use of what's called a harmonic restraint. And so if you have an overcurrent function, what you're going to do is you're going to be generating another signal where this is going to be looking at second harmonics or fourth harmonics or possibly fifth harmonics. And then depending on the amount of harmonic content, you actually keep the overcurrent from tripping. In other words, you kind of have a restraint signal that basically says to your logic, hey, I see this large second harmonic or fourth harmonic component. I'm probably energizing a transformer right now, and I want to make sure I don't trip unnecessarily on overcurrent based on this. So anyway, here's what I'll be going through for the worked example, and I'll leave this till later.